Welcome. In this poster, I will be describing the NRGTEN and dynasigML Python packages. These are fast and user-friendly tools that can be employed for a variety of purposes, including protein engineering. You can read all the text of the poster, but in brief, what NRGTEN allows you to do is have the structure of a biomolecule, and that can be a protein, a nucleic acid, with or without small molecules and complexes, generate an elastic network model. And in this case, the NRGTEN toolkit allows you to utilize a number of different models, elastic models, including NCOM, which is the one that we develop, and it's the only one that takes in consideration the chemical nature of the interacting atoms in the generation of the nodes and the edges, and that allows it to be sequence sensitive as opposed to other methods such as ANM, which is widely used, but it's purely geometric, the criteria for the creation of the edges. You can also create your own custom elastic network. With elastic network defined, you can then generate the normal modes. In here, in this figure, I'm showing only one normal mode, the first one, the first non-trivial one. And as you can see from the arrows, one normal mode is a set of movements that are non-localized. In other words, one normal mode affects the movement of every node, which in this case, for this protein, a node represents an amino acid. And with the normal modes, a number of things can be done. Dynamical signatures can be calculated, and here you have a vector where the x-axis represents the position in the sequence, whereas the y represents the amount of flexibility that that residue can potentially experience once the effect on that residue of all the normal modes acting on that residue are taken in consideration. A second application is the generation of conformational ensembles. The normal modes can be used in linear combination to generate actual movements, and this can be used to generate a conformational ensemble. And these conformational ensembles can be used in a number of ways. For example, to study conformational transitions, to generate ensembles for docking, and for protein engineering, as I will discuss in a moment. Another application is to calculate the vibrational entropy differences between two states, and this allows you to calculate when you have a mutation, if it will lead to rigidification or flexibilization, I don't know if that is a word, of different areas of the protein, affecting the function and as a whole affecting the stability. Now, the last application that is shown here is that with the normal modes, all of them taken together, we can actually see if not only if a residue is flexible or rigid, but also if the movements tend to go towards a direction that would lead you from one state to another, and so the normal modes may favor one state over another, and so we can calculate transition probabilities between states. All of this is the NRGTEN package. When you use the NRGTEN package with NCOM, which is sequence sensitive as opposed to the other elastic networks, you can, for example, start with a protein structure, perform in silico mutations, and compute the dynamical signatures. All of this is done automatically within the dynasigML package, and use it to train both a lasso linear regression model as well as a multiple linear a multi-layer perceptron. And the training that the data that you use to train can be any function that is measured experimentally for a large number of these mutations. For example, in this case, for the VIM2 lactamase, it is the fitness, the evolutionary fitness conferred by the mutation, and some make the enzyme more resistant to antibiotics. Some make the a bacteria that would contain this enzyme more resistant to antibiotics, others less. And so what's interesting here is that the lasso linear regression, because it's linear, it allows you to map the effect of these coefficients, or the importance of the flexibility at each position, towards predicting higher different levels of the function. And this may allow you to generate hypotheses to understand your experimental system. The second thing that can be done with the dynasigML package is to generate a multi-layer perceptron, and that in general attains higher prediction accuracy, or it has higher predictive power than a linear model. In particular, we can think that because the normal modes and their effect in flexibility is widespread, it's not linear, then a non-linear model like a perceptron can capture this more efficiently. So what applications can you have in terms of protein engineering? So we can use this to increase the thermal stability of proteins. We showed this in comparing mesophile and thermophile proteins. Of course, not the entirety of the effect that leads to thermal stability is entropic, but capturing the entropic part of it allows in great extent to explain stability, and also to select, in case if you are doing protein engineering, to select those mutations that do have an entropic origin to their effect in increasing the stability. You can generate conformational ensembles and use it in computational protein design. We don't do that, but many groups around the world use conformational ensembles to improve the quality of computational protein design. And this is something that you can do here, as opposed to, for example, using molecular dynamics, or in addition to. Can I select mutations that increase stability but do not affect binding site flexibility? Yes, you can. You can select mutations that increase stability while keeping in check the pattern of the dynamical signature to match that of the wild type, for example. Can I modulate the transition probability between conformational states and thus affect function? Yes, we've done that studying the spike protein in SARS-CoV-2. You can take a look at the paper in PLOS Computational Biology. Can I study the structural determinants of protein function? This is exactly what we did here with the VIM2 beta-lactamase. And because you can map them on the structure, you can understand what areas of the protein affect function and how they affect. For example, the red areas may affect, may increase the evolutionary fitness in general. So most mutations here do that, whereas most mutations in this blue area decrease the fitness. So that allows you to understand function. Can I use experimental data to engineer function? Yes. Once you train your multi-layer perceptron, you can then challenge it with new mutations that were not used in training, and predict their effect. And what else can you do? Well, you can do whatever comes to your mind with our tools, and I'm looking forward to see what you can do with it. And perhaps this citation here will be your name in the future. How to get these tools? The poster has QR codes. We have GitHub packages describing them, and we have also documentation with step-by-step tutorials on how to use dynasig, as well as NRGTEN. So with that, I thank you for your attention, and if you have any questions, please reach out. Bye bye for now.